Ever stared up at the sun and felt its warmth on your skin? It feels like a constant, unchanging force in our lives, right? But what if I told you that our sun hasn't always been the bright, powerful star we know today? Billions of years ago, it was much, much fainter. This simple fact presents one of the most fascinating puzzles in Earth's history, the faint young sun paradox. Let's travel back in time, way back, about 4 billion years ago, during the Archean. Our planet was young, and life was just beginning to take its first tentative steps in the primordial oceans. According to everything we know about how stars like our sun evolve, the young sun was only about 75% as bright as it is today. That's a huge difference. With so much less solar energy reaching us, you'd expect the Earth to be a frozen wasteland, a giant snowball in space. The ocean should have been solid ice, making it incredibly difficult, if not impossible, for life to arise and thrive. But here's the paradox. The geological evidence tells a completely different story. We've found ancient rocks, some dating back 3.8 billion years, that show clear signs of liquid water. There are pillow lavas, which only form when molten rock cools rapidly underwater. There are sedimentary rocks that could only have been deposited by flowing rivers and settled in ancient seabeds. Even more compelling, we have fossilized stromatolites, layered structures built by ancient microbes, which prove that life not only existed, but was flourishing in liquid oceans. So, we have a major cosmic contradiction. On one hand, astrophysics tells us the sun was too dim to keep the Earth warm. On the other hand, geology and paleontology tell us the Earth was warm and wet. How can both be true? How did our young planet avoid becoming a permanent ice world? This is the core of the faint young sun paradox, a puzzle that has challenged scientists for decades. It forces us to rethink everything we know about planetary atmospheres, climate, and the delicate balance required for life. To solve this mystery, scientists had to look beyond the sun and focus on the Earth itself. The answer, most believe, lies in Earth's early atmosphere. It must have been very different from the air we breathe today, which is mostly nitrogen and oxygen. The leading theory is that the young Earth had a much stronger greenhouse effect. A super greenhouse effect, in fact. So, what gases were responsible for this planetary blanket? Carbon dioxide, or CO2, is the prime suspect. Computer models suggest that if the early atmosphere had hundreds or even thousands of times more CO2 than it does today, it could have trapped enough of the faint sun's heat to keep the oceans liquid. This makes sense. In the early days of our solar system, volcanic activity was far more intense than it is now. Volcanoes spew out enormous amounts of gases, including CO2, with no continents and no complex life to absorb it. This CO2 would have built up in the atmosphere, creating a thick, heat-trapping blanket. But CO2 might not have been working alone. Another powerful greenhouse gas could have been in play: methane. Methane is over 25 times more potent at trapping heat than CO2, although it doesn't last as long in the atmosphere. Early life on Earth, specifically methanogens, microbes that produce methane as a byproduct of their metabolism, could have been pumping this super potent gas into the atmosphere. Imagine tiny single-celled organisms collectively changing the climate of an entire planet. A combination of high CO2 from volcanoes and methane from early life could have easily provided the extra warmth Earth needed to stay habitable. However, relying on a methane-rich atmosphere presents its own set of problems. Methane is chemically fragile. When exposed to ultraviolet light from the sun, it can break down and form a thick organic haze similar to what we see on Saturn's moon, Titan. This haze would have acted like a planetary sunscreen, reflecting sunlight back into space and actually cooling the planet down. This is called an anti-greenhouse effect. So, there had to be a delicate balance. Enough methane to warm the planet, but not so much that it created a haze that would cool it. Some scientists even propose that a bit of haze could have been beneficial, shielding the fragile, early life forms from the sun's harsh UV radiation. As the puzzle became more complex, other theories emerged. Perhaps the Earth's albedo, its reflectivity, was lower back then. A darker planet absorbs more sunlight. With fewer continents and more dark, open ocean, the young Earth would have naturally absorbed more solar energy than our current world, with its bright ice caps and sprawling land masses. Another idea involves clouds. Certain types of clouds, like thin, high-altitude cirrus clouds, are excellent at trapping heat. If the early Earth had a different cloud composition, it could have contributed to the warming. Then there's the cosmic perspective. What if the sun wasn't the only source of heat? Our planet has its own internal heat engine, powered by radioactive decay in the core. While this geothermal heat is significant, most scientists agree it wouldn't have been nearly enough to warm the entire surface on its own. A more radical idea suggests that our sun might have been slightly more massive in its youth. A more massive sun would have been brighter, potentially solving the paradox. However, it would have had to lose just the right amount of mass over billions of years through a stronger solar wind, and the evidence for this is still debated. So, as our sun gradually brightened over billions of years, what happened to this super greenhouse atmosphere? The story of how Earth's climate stabilized is just as fascinating. As life evolved, a new player entered the scene: photosynthetic organisms. These microbes, like cyanobacteria, learned to harness sunlight for energy. In doing so, they consumed vast amounts of atmospheric CO2 and released a waste product, oxygen. This was the Great Oxidation Event, a pivotal moment in Earth's history around 2.4 billion years ago. The rise of oxygen had dramatic consequences. It reacted with the atmospheric methane, drastically reducing its concentration and weakening the greenhouse effect. This event, nicknamed the oxygen catastrophe, was so profound that it likely plunged the Earth into its first major ice age, a period known as the Huronian glaciation. The planet may have finally frozen over, becoming the snowball Earth it had avoided for so long. But life is resilient. Over millions of years, a new balance was struck. Volcanoes continued to pump CO2 into the atmosphere, while geological processes like weathering of rocks started to regulate it, creating a long-term climate thermostat. The sun continued its slow march towards its current brightness, and Earth's climate system co-evolved alongside it. The planet thawed, and life continued its journey toward more complex forms. The faint young sun paradox isn't just an ancient history lesson. It has profound implications for our search for life beyond Earth. When we look at exoplanets orbiting other stars, especially younger, dimmer stars, we can't just consider their distance from the star. We have to consider the potential for a powerful greenhouse atmosphere to create habitable conditions. A planet that looks frozen from a distance might actually have liquid water and life hidden beneath a thick blanket of CO2 and methane. This paradox has fundamentally expanded our definition of a habitable zone. So, while we haven't found a single, definitive answer, the investigation has taught us so much about the incredible resilience of our planet. It reveals a world in constant flux, where geology, biology, and astronomy are all intertwined in a delicate dance that has lasted for billions of years. The fact that you and I are here today is a testament to that incredible balancing act. Our planet didn't just get lucky, it had a dynamic, self-regulating system that allowed it to navigate a cosmic challenge and become the vibrant world we call home. Thanks so much for joining me on this journey back in time. It's a humbling reminder that our world has been shaped by forces we're only just beginning to understand. If you found this cosmic mystery as fascinating as I do, please hit that like button and be sure to subscribe for more deep dives into the wonders of our universe. Let me know your thoughts on the faint young sun paradox in the comments below. See you next time.